Now, in our analysis of fluid dynamics, we've thus far been dealing with ideal fluids. That means frictionless. But of course, fluids aren't ideal, nothing is. And so how do we model friction with fluids? Well, the fluid as it flows through a pipe will tend to stick to the walls. That means that there needs to be a net force to move it through. That means that the pressure on this side must actually be a little bit bigger than the pressure on this side. Or in other words, that there's a loss of pressure over the length of the pump. This change in pressure, this loss in pressure, is sometimes called head loss. Now, we expect the head loss to be greater if you have a smaller pipe. So that suggests that the head loss should be inversely proportional to the radius of the pipe. So that if this radius gets smaller, then the fraction's larger and you have a larger head loss. We also expect that if you're trying to force more fluid through, then the head loss would increase. So the head loss should vary with the volume rate of flow. Now, there's a couple of cases of fluid flow that affect the precise formulation of this head pressure head loss. First of all, if the fluid is smooth and the fluid flow is smooth and laminar with no turbulence, then the head loss is best represented by Poiseuille's law. Poiseuille's law says that the head loss, the drop in pressure over the pipe, varies directly with the volume rate of flow and also depends on, okay, the eight's just a constant, this is the viscosity coefficient of the flowing fluid, this is the length of the pipe, and we knew that it had to vary inversely with R, but it actually varies inversely with the fourth power radius when you have laminar fluid flow. This is a Greek letter eta, it's the viscosity coefficient of the fluid. And these are just constants which are given. Now water has 1 times 10 to the minus 3. Something a lot thicker like motor oil is 0.6. So you can see that more sticky fluids have higher viscosity coefficients. Let's do, first of all, note that because the pressure drop is just some constant times the flow rate, this is like y equals mx plus b. So this should just be straight line direct variation. Sorry, that's supposed to be a straight line. That's horrible. Let's do that. Here, I'll use the straight line drawer. There we go. Voila. And the value of that slope should just be this set of numbers, 8 eta L over pi r to the 4th. I guess you could put a plus 0 now, right? Remember, y equals mx plus b. So if you plot pressure drop versus volume rate of flow, with pressure drop on the y-axis, rate of flow on the x-axis, you should get a slope that's this number, and you should get a y-intercept of 0. So that's what we'd expect if we had laminar flow. Let's do a quick calculation with that. Okay, so this is the bladder, and it squeezes, pushes on the urine, and then the urine flows out. Now, because of viscosity, as it flows through the ureter, or the urethra, there's going to be a drop in pressure. And if that flow, again, is laminar, the drop in pressure will be given by Poiseuille's law. Okay, so let's see. So we've got the radius, 2 millimeters, 2 times 10 to the power minus 3. The length is 30 centimeters, that's 0.3 meters. Now the viscosity is 15% greater than water. So that means it's 1.15 times the viscosity of water, or 1.15 times 10 to the minus 3 power. Now I didn't mention it earlier, but the units of viscosity are pascals times seconds. Now the rate of flow, the volume rate of flow, is given as 10 milliliters per second. Now in order to do calculations with meters and pascals, etc., this needs to be in cubic meters. So first we'll convert to liters. A liter is 1,000 milliliters, and then we need to convert again to cubic meters by dividing by 1,000 again. So the answer is this is 1 times 10 to the power minus 5 cubic meters each second. So now we can calculate that pressure head So we'll substitute in everything with the units, because we usually do the calculations with units at least once, just to show it all works out. Okay, so this is going to be meters to the power of 4. So this meters to the 4 will cancel off that meter and that meter cubed. And then the second cancel, and so the units just emerge as pascals, which is good because it's a pressure. And then we calculate, so it's 8 times 1.15 E3 negative times 0.3 times 1 E5 negative, divide by pi, and divide by, on this crummy calculator I've got to do a bracket, 2E3, change sign, then I close the bracket. Now fourth power, I could do y to the x to the power of 4, or I could just square it, and that's kind of cute. Squaring it twice is fourth power. And so we get the answer of 549 Pascal pressure drop. So you need 549 pascals of net pressure on that urine to move it out of the ureter in that amount of time. Okay, that was for laminar flow, we said, right? That head loss formulation. What if the flow isn't laminar? What if it's turbulent? Well, then the head loss is given by, better pause the video there, we've had a problem. Okay, we're back on stream there. Brief technical pause. So if the flow is turbulent, then there's another relationship that governs the head loss. It's known as the Darcy-Weisbach equation. And in this case, the pressure head actually varies with the square of the volume rate of flow. Now, there's the usual suspects. It does, of course, vary inversely with the radius. So that's actually a square on the pi. That's the power of 2. So it varies with the inversely with the radius, but radius to the 5th power in this relationship. It varies with the length, the density of the fluid that's flowing, and then there's a sorry, a constant known as the Darcy factor, and that depends on what the pipe's made of and how sticky it is for that fluid. So because we have the head loss varying with the square of flow rate, if you were to plot head loss, you'd get a parabola. So what we do instead in the lab is we plot head loss versus the square of flow rate. Then that's on the y-axis, this is on the x-axis, then this should be the slope, and it should be another straight line. It should go through, let's draw that line more precisely, there we go through the origin, and this would be the expected slope. Let's do a calculation. So if we have turbulent flow, then the amount of head loss, so this is flowing oil in a pipeline, will be given by the Darcy-Weisbach equation, just transcribing it from earlier. Okay, so let's see what we're given. So we're given the radius, 0.2 meters, flow rate, that'll need to be converted. This is 2,000 liters per minute. So I just paused that to cough. I know it's horrendous listening to me cough. So that'll convert from minutes to seconds. Then we need to convert cubic meters from liters to cubic meters. So this works out to 0.03 repeating cubic meters each second. So we're also given the length, it's 50 kilometers. The F factor, and we're given the density of the crude that's flowing through the pipe is 920 kilograms per every cubic meter. Okay, so now we can calculate what that head loss would be. 1, 50,000 for the length, 920 for the density. And I'm not going to put units in just because I did a similar calculation. So let's work out what this is. 0.01 times 50,000 times 920, divide by 4, divide by pi again, divide by 0.2 of 5, and multiply that by 0.03 repeating. I'll just put in a bunch of 3's. Oh, sorry. Yes, that's I made a mistake up here. Ha ha ha. That's why I'm not getting the right answer, because yes, it varies with that square, doesn't it? So we have to multiply by 0.03 again. Times 0.03. And now we get the expected answer of 40,000 pascals, 40 kilopascals. Okay, so it's dropped by about half an atmosphere there, about by 7 psi. So every once in a while you need to pump it up again, and that's why they need compressor stations along pipeline runs. So these are the two principles then of fluid flow with friction that we'll be looking at in our lab this week.